Picture this. Your level looks incredible in the editor. Every bounce of light, every reflection, exactly where it should be. You hit play, target 4K, and your frame counter falls off a cliff, 30 frames per second, on hardware that should be doing far better than that. If that's ever happened to you, what you just watched wasn't a bug. It was the real, measured cost of ray-traced global illumination in Unreal Engine 5 today. We've spent months chasing that exact wall in our own projects, and by the end of this video, we're going to show you the number on the other side of it, 42 frames per second, in that same scene, at that same 4K resolution, a 40% gain without giving up the ray-traced reflections your project actually needs. Here's how we got there. This is Voxel Global Illumination, or Voxel GI, a plugin built for Unreal Engine 5 developed here at Pterosoft Studio. Over the next 20 minutes, we're going to walk through why we built it, how it actually works under the hood, what it costs and what it saves you in frame time, and where you can get it today. Let's get into it. Let's start with the honest question. Unreal already has Lumen. Why build a second global illumination system at all? We landed on 4 reasons, and we want to walk through each of them properly, because none of them are a knock on Lumen. They're a description of where its edges are. First, performance. Full ray-traced global illumination is still heavy. Hardware ray tracing has come a long way, but tracing coherent, denoised, temporally stable rays across an entire scene, every frame, at native resolution, is still one of the most expensive things you can ask a GPU to do. Lumen's software ray tracing mode gets around some of this by working on a simplified scene representation, and its hardware mode leans on RT cores, but both of them carry real cost, and that cost scales with scene complexity in ways that aren't always predictable. If you've shipped a Lumen lit level, you already know this. You spend as much time budgeting GI cost as you do art directing the lighting itself. Second, Lumen only does limited specular tracing. This is a subtler point, but an important one for anyone doing anything reflective. Wet streets, glass, metal, water. Lumen's reflections are good, but they're built on the same underlying GI infrastructure, and there are real limits to how far and how accurately it traces specular paths, especially on rough or highly reflective surfaces at distance. Teams doing anything visually ambitious with reflective materials often end up supplementing Lumen with additional systems anyway: reflection captures, screen space fallbacks, planar reflections for hero surfaces. We wanted a GI system where specular tracing wasn't an afterthought bolted onto a diffuse solution. Third, open world titles struggle with Lumen's performance specifically. This is where the cost problem becomes existential rather than just annoying. Open world games already have the tightest performance budgets in the industry. You're rendering enormous draw distances, huge amounts of foliage, streaming systems, NPC counts, all competing for the same frame time. Add Lumen's GI cost on top of that, at the resolution and frame rate console platforms expect, and a lot of open world teams find themselves either scaling back GI quality dramatically, capping resolution, or spending enormous engineering effort just to keep Lumen affordable at scale. We wanted a system that behaves differently under those exact conditions, and as we'll show you in the performance section, it does. Fourth, and maybe most important, more options for players and developers. This is really the philosophy behind the whole plugin. We don't think there should be one correct way to light a scene in Unreal Engine 5. Different games have different visual targets, different hardware floors, different performance philosophies. Some studios want the flexibility Lumen offers, others want a GI solution that trades some of that flexibility for raw throughput, or that behaves more predictably across a huge range of GPUs, including hardware where ray tracing isn't a realistic option at all. Voxel GI exists to be that second option, not a replacement, an alternative sitting right next to Lumen in your project settings. So let's open the hood. How does Voxel GI actually produce a lit image? It handles both diffuse and specular GI. Unlike a lot of legacy GI techniques that only solve the diffuse bounce, the soft, even light bleeding around corners, Voxel GI computes both halves of the lighting equation. Diffuse GI gives you that indirect bounce lighting, color bleeding, ambient occlusion-like darkening in corners. Specular GI is what gives you indirect reflections, light bouncing off a shiny floor, a chrome surface picking up the environment around it, even when that environment isn't directly visible to the camera through a mirror-perfect reflection capture. The scene geometry is voxelized. This is the foundational idea, and it's actually a technique with real pedigree. Voxel cone tracing was pioneered in academic and industry research over a decade ago, most notably by Cyril Krassen's work, and it's been used in various forms across the industry since. Instead of tracing rays against the actual triangle mesh of your level, which is expensive and doesn't scale well, we convert the scene into a voxel representation. Think of it as taking your level and re-expressing it as a 3D grid of small cubes, each one storing lighting and occlusion information. Once your geometry lives in that grid, querying, what does the light look like in this general direction from this point, becomes dramatically cheaper than tracing against raw triangles. Lighting is gathered using cone tracing. This is the technique that gives voxel cone tracing its name. Rather than firing a single, infinitely thin ray per sample, which is noisy and needs heavy denoising to look clean, we trace a cone. As that cone travels through the voxel grid, it widens, and at each step, we sample a correspondingly larger region of voxels, essentially pre-filtering the result as we go. This naturally produces soft, physically plausible falloff for indirect lighting and reflections. And critically, it's inherently more stable than single-ray sampling, which means less reliance on aggressive temporal denoising and fewer of the smearing or disocclusion artifacts that denoisers can introduce. That voxel data is organized in a sparse octree for maximum performance. Here's the thing about voxelizing an entire level. If you stored a uniform, dense grid of voxels across your whole world, you'd burn an enormous amount of memory and bandwidth on empty space, sky, air, the inside of solid rock nobody will ever see. A sparse octree solves this by subdividing space recursively, but only where there's actually geometry that needs representing. Empty regions stay coarse or don't get allocated at all. This is what lets Voxel GI scale to real production-sized levels without the memory and performance cost exploding the way a naive, dense voxel grid would. By default, GI is traced at half resolution, and that's adjustable. This is one of the primary levers we give you for balancing quality against performance. Global illumination, by its nature, is low frequency. It doesn't need the same pixel-perfect precision as your primary geometry or your direct lighting. So by default, Voxel GI computes its diffuse and specular indirect lighting at half the screen's native resolution, then upsamples intelligently to full resolution before compositing. On most content, this is visually indistinguishable from full resolution tracing, but it roughly halves the GI workload. And if a project specifically needs full resolution GI, maybe a slower paced game where every reflection needs to be razor sharp, that resolution scale is exposed and adjustable in the plugin settings. And for reflective surfaces specifically, we layer in RT specular tracing. This is where Voxel G1 hybridizes with hardware ray tracing rather than replacing it outright. Cone tracing through a voxel structure is excellent for broad, soft indirect lighting and rough reflections. But for sharp, high-fidelity reflections on glossy or mirror-like surfaces, the kind where accuracy really matters to the eye, we bring in dedicated ray-traced reflection tracing on top. So you get the performance and stability of voxel cone tracing for your G1 backbone and the precision of RT reflections exactly where the human eye is most sensitive to error. It's not one technique pretending to do everything, it's the right tool applied to each part of the problem. Numbers matter more than architecture slides, so let's talk about what this actually costs you in frame time. Voxel GI excels specifically at high resolution, and that's worth explaining because it's counterintuitive. You'd expect any GI system to get more expensive as resolution climbs, and in absolute terms, it does. But relative to Lumen, the gap widens in Voxel GI's favor as resolution increases. Here's why. Higher output resolution means more rays and samples are needed to maintain equivalent visual quality. And that's exactly the kind of workload cone tracing through a sparse octree is built to absorb efficiently. It scales more gracefully than Lumen's tracing pipeline does under the same conditions. So the more demanding your target resolution, the bigger the advantage becomes. In our benchmarks, at 1080p, we measured 110 frames per second with Voxel GI versus 85 frames per second with Lumen in the same scene under the same lighting conditions. That's a substantial gap even at a relatively modest resolution. At 4K, that comparison becomes 42 frames per second with Voxel GI versus 30 frames per second with Lumen. 30 frames per second at 4K is the kind of number that puts a project uncomfortably close to being unplayable on console, or forces aggressive dynamic resolution scaling to compensate. 42 frames per second gives you meaningfully more headroom for additional post-processing, higher NPC counts, denser foliage, whatever your project actually needs that budget for. Put in relative terms, that's roughly a 25% performance improvement at 1080p, and roughly 40% at 4K. And that 40% figure at 4K is really the headline number here. As display resolutions climb, and they are climbing both on PC and on console with performance modes increasingly targeting 4K output, the performance advantage of Voxel GI over Lumen doesn't just hold, it grows. For any team specifically targeting high-resolution output, whether that's a visually driven PC title or a console game chasing a 4K performance mode, this is the exact scenario where switching your GI backend pays off the most. So, where can you actually get this, and what does it take to drop it into your project? Voxel GI is released as a plugin. This isn't a fork of the engine, and it's not something that requires you to rebuild Unreal from source with custom patches. It installs the way any other Unreal Engine plugin does, and it's built to sit alongside Lumen in your project, not replace your rendering pipeline wholesale. You can enable it per project, and in many cases, toggle between it and Lumen to compare directly in your own content. It's available on Fab, Epic's official marketplace for Unreal Engine assets and plugins, so it goes through the same distribution channel, licensing, and installation flow you're already used to for any other marketplace plugin. It's priced at $149.99. It was built and validated against Unreal Engine 5.7, but it also works with 5.8. We know engine version compatibility is a real concern for any team evaluating third-party plugins. Nobody wants to lock themselves out of engine updates because of a tooling dependency. We'll continue to track new engine releases as they ship. And for full documentation, setup guides, and more technical detail than we can fit into 20 minutes here, visit unrealvoxel.pterosoftstudio.com. That's where you'll find the complete breakdown of every setting we've mentioned today. The resolution scale, the octree configuration, the RT reflection toggles, along with integration notes for teams migrating an existing Lumen lit project over to Voxel GI. That's Voxel Global Illumination. Why we built it, how it works, what it costs in frame time, and where to find it. To recap in one line, it's a voxel cone-traced GI system for Unreal Engine 5 that trades some of Lumen's flexibility for meaningfully better performance at high resolution, with hardware ray tracing layered in specifically where reflections need it most. Thank you for watching. Please like, share, and subscribe. It genuinely helps a small studio like ours reach the developers this is actually built for. If you have any questions, type them below. We read every comment, and we're eager to hear what you think, especially if you've been fighting with Lumen performance on your own project and want to know whether this solves your specific case. You can also follow us on Bluesky at @pterosoft.bsky.social for ongoing updates, and find everything else we do at www.pterosoftstudio.com. Thanks again for your time.